Excuse me, sir. Am I audible?
Yeah. Yes, you are audible. You can ask.
No, nothing to ask. I just wanted to make sure. Actually,
Okay.
I'm traveling right now, so
Yeah. So welcome to week 2 of the MA106 category theory course. I am Shubhajit. I am a PhD student at the Department of Mathematics, and each week we solve problems from the lectures that you attend in the NPTEL platform. And previous week we previous week you saw what categories really are. You were exposed to the philosophy of category theory as an alternate foundation to mathematics, set theory being the usual one. And last week there were some problems that we left out, so I won't exactly be solving the rest of the problems except one of them. I'll leave the all the other problems as homework problems or practice problems for you. If you have any questions based on them, you can ask me, but for now I'll just leave them as practice problems. So these are available on the, I don't exactly know where this uploaded, but I'm sure you can access them.
yes, sir.
Yeah, so we'll start with this problem and then come to the material of this particular week. But so you can see the problem exactly. It says it's a true or false statement. So C is a category. You just need to identify whether the statement mentioned here is true or false. So C is a groupoid if and only if every diagram in C of this form. So there is an object A, there is an object B, there is an object C. From A to B you have an arrow F. From A to C you have an arrow G. Every such diagram can be completed to a commutative triangle like this. So there should exist an arrow H from C to B, making this particular triangle commute. By which we, all that we mean is that H composed with G should be equal to F. So is this statement true or false? That a category C will be a groupoid if and only if this property or this statement holds, that given any diagram in C of this form, it can always be completed to a commutative triangle in terms of the existence of an arrow H from C to B, making the triangle commute. So what do you think?
True.
It's true, okay. So we'll come to this. Let others try first. What do others think of this? So a category is a groupoid if and only if every diagram in C of this form can be completed to a commutative triangle like this. Okay, why do you think it's true, Nisarg?
One direction I was thinking was that Gx is equal to F always has a solution inside a group.
Okay, I see. Okay, So that was, I mean, that was an, so that is an intuition that you have, but I
Yes,
mean,
yes.
it's sort of in the correct direction. But can you give me a concrete proof? So what is
Then
exactly a group art? It's a category in which every arrow is invertible,
is
right?
huh.
That is, every arrow is an isomorphism actually. Every arrow is an invertible arrow. That is an isomorphism. So yeah. So how do you conclude this, or how do
And
you?
then there was also this thing where if you take f to be the identity function, then this guarantees the existence of right inverses. Oh, sorry, I think left inverses.
Okay, so first of all, we claim that statement is true, and how do we show? So we need to show that every arrow has an inverse. That is, every arrow should be invertible. So we take an arbitrary arrow from some object A to some object B, F, let's say. We want to show that this arrow, that is this morphism F, is an isomorphism. So you want to show that it has an inverse. Yeah. So how exactly do we show this?
Okay, so if we take a to a the identity function.
A to A identity. First of all, don't call it a function, because this is just an abstract symbol, right? It's just an arrow. It's supposed to mimic or capture the idea that there is some kind of some kind of a map. So it's better to
Got it.
call it a morphism or an map or an arrow, if you like, because this A and B are not sets, right? They are just abstract objects in a category. Yeah.
Right.
So one A from A to A, the identity arrow, and
Then this condition in the question guarantees that there exists g such that g of f is equal to 1a.
okay. So and we also take our F from A to B. This is what you mean, right?
Yes.
So by the given condition, this horn can be filled up by the existence of an arrow G from B to A, such that G composed with F is 1A. Fine. So F has a left inverse G. How do you show that F also has a right inverse? So far we have only shown that F is left invertible. That is something you'll learn in the next week, that an arrow is called a split monomorphism if it's left invertible. But yeah, so far G is a left inverse of F. We also want to show that F has a right inverse. How do you show that? We can just start with, so we have a G. So F has, we want to show F has a right inverse. So far we only know F has a left inverse G. So we know G itself has a right inverse, right?
Right.
So what can we do? We can start with G itself, right? See, if F is a right inverse of G and you want to show that F also has a left inverse, I mean, sorry, if sorry, we already have F has a left inverse G. If you want to show that F has a right inverse, what do you think that inverse should be? That right inverse should be
G itself.
G itself, right? So that means we only know so far. Now think everything from the perspective of G. G has a right inverse F. We now want to show that G also has a left inverse, right? So we can just start with, and
Okay.
this procedure of filling up the triangle actually creates left inverses. We want now a left inverse for G as well. So start with G itself. G is from B to A, that we know. Again we take this diagram. So what should we take? We should take B to B, the identity morphism 1A, and B to A we take G, right? So B to B 1B, and we take G. So again, by our uh, property, or whatever this process is, there exists some arrow H from A to B such that H composed with G is 1B. Okay. Now this is exactly the situation that you have in groups. So we'll come to this. So what exactly are the two equations so far? So first of all, you know that G is a left inverse of 1A. G is a left inverse of F, and H is a left inverse of G. So G has a right inverse F and G has a left inverse H. We want to show that F is equal to H, and then we are done. This is conclusive proof of the fact that F has an inverse and it's G. So how to show that these two are equal, F and H are equal?
We consider H compose decompose F.
Yes. And just give me the precise word that, or the precise property that you are using here to conclude this.
Associativity of function.
Yes.
Composition.
Associativity of composition. You don't have functions again. These are just
Right,
abstract objects and abstract arrows. So yeah, associativity of composition. So in a category, objects are to be treated as primitive notions, right? There is no internal structure. That is why we'll just refer to them as objects, and we'll just call the arrows to be arrows or morphisms, if you like. So yeah, we start with H composed G composed F, with a bracket on G composed F. Now G composed F was identity on A, so this is H composed 1A. And what is that?
H.
That's just H. And now we can use associativity here. So this is where we are using associativity to have H composed with G composed with F, right? Now what is H composed with G? It's 1B composed with F, which is F. And that basically proves that H is equal to F. So what you have is, for the arrow F A to B, there exists a G in the opposite direction B to A, such that G composed with F is 1A, and F composed with G, since F is equal to H, is 1B. So the arrow F has this special algebraic property that this arrow F is an isomorphism. In the category C. And F was just an arbitrary arrow that we started with, right? So C is a groupoid. The category C is actually a groupoid. Right. Pretty simple so far. In fact, this characterization of groupoids is perhaps a pretty deep characterization, but we won't get into the details of that. Okay, so coming to this week, so let's just make a small or a short summary of what actually you learned, or rather the philosophy of it. Oops. So in this week, so in week 2, you learned that so this is something that you already understand intuitively, that a category is a mathematical object in its own right. So it is natural to consider the question, is there a sensible notion of map in the context of categories? And you saw that the answer to this question is in the affirmative. So yes, a map of categories is called a functor. But this is not just where you stop, right? Perhaps surprisingly, there is a further notion of map in the context of functors. So basically, you change your perspective, and instead of thinking as functors as maps of categories, you think of functors as mathematical objects themselves. So this is one functor f, and this is one functor g, and you can now talk about a map from the functor f to the functor g, which is exactly called a, what is it called?
Natural transformation.
Yes. So such a map is called a natural transformation. But I mean, it would be good if we could continue, but the structure of a category is allows you to do this much, up to this much. You can talk about a natural transformation. You have to stop here, unfortunately. Okay, so this is the content of this particular week, and we'll be solving problems based on this. Okay. So let's start. Yeah, I should also mention this, that sorry, let me just check if it's still recording. Yeah. And you also learned that there is a notion of equivalence of categories, right? I mean, usually, so the shift in perspective from set theory happens like this, like, so further there is a notion of equivalence of categories. So the idea is, in a set, the right notion of comparing two elements, or I should say the right notion of sameness of elements is equality. In a category, the right notion of sameness of objects is not equality, because equality is too strict in the context of a category. So it's an isomorphism. Equality is too strict. And in the context of categories, of course, we can ask about isomorphisms of categories, right? So given two categories, we can ask for a functor f from the first category to the second, together with a functor in the opposite direction, such that these two compose to give you identity functors. That is what an isomorphism is. In other words, an isomorphism of categories is exactly an isomorphism in the category of all categories and functors. But then again, that's a strict notion of sameness, right? So in the context of categories, isomorphism of categories is too strict, right? Because what would that mean? So C is isomorphic to D would mean that there is a functor C to D, which we call F, and there is a functor G, D to C, such that G composed F is 1C and F composed G is 1D. And what does that mean? That in particular means that that in particular for every object A in C, G of f of C, G of f of A is A, right? Is exactly equal to A. Now A is an object in C and G of f of A is also an object in C. And we are asking for the equality of two objects, which is a level of detail that we have just sort of declared ourselves to be too strict, right? Equality of objects is something we don't want. We want the notion of an isomorphism, right? So this is too strict. Which is why what you want the notion of equivalence of categories. So given categories C and D, an equivalence of categories from C to D is a functor f together with another functor in the opposite direction, which compose and such that the compositions are naturally isomorphic to the identity functors. This is the correct notion of sameness of categories, right? Okay, so with that in mind, we'll start the problems of this week. Okay, so we know that the category GR of groups has group homomorphisms as its arrows, right? I mean, it's understood because the right notion of structure preserving maps in the context of groups are exactly group homomorphisms. So the category GR of groups should have group homomorphisms as its arrows. So I ask you this question: what happens if instead the objects are still taken to be the category, are still taken to be groups, but if instead the arrows are just taken to be set mappings? Of course, every group is a set, so you can take any set map from one group to another group, right? So what happens if the category has set maps as your arrows? So what do you think? By the way, feel free to stop me if you have any questions at any point. What do you think? So this is a conceptual question, and we want to investigate what happens if group homomorphisms are just replaced by set maps as the arrows of your category. So certainly intuitively this doesn't seem to be very useful in the sense that the maps no longer use the structure of the groups, right? The group structures are not used or rather preserved by maps. But can we say something concrete here? What do you think? So what I'm trying to say is we are creating an auxiliary category C whose objects, so we are creating a category C whose objects are groups, whose arrows are set maps. Composition is usual composition of set maps. Identity is identity map. But this has an issue.
The initial and terminal objects will change.
Fine, let them change. I mean, that doesn't really matter much, right? What I'm asking is, considering this category would be useless in a certain way. And why am I saying that it's useless? What do you think? Or rather, working with this category is no longer is not fruitful, or rather it's something that you have previously already considered in a certain sense. So this is not something new. That is what I'm saying. That is your hint. This is not a new category. What do you think?
You could say that this is like a.
I'm sorry, can you
already
be a bit louder?
So we can just think about this as a subcategory, even though that's not defined, but like it's already the category of sets.
So keep in mind that a set can have many group structures, right? For example, a 4-element set can have 2 different group structures. So this is not exactly a subcategory, strictly speaking, of the category of sets and maps, but you are very close. It's pretty much related to the category of sets. So what exactly are we trying to say here?
Is this equivalent to the category of sets?
Yes, you are still very close. I mean, completely close. So this is not a new category. That is what we intend to say, in the sense that this category is equivalent to some category of sets, not just the category of all sets, equivalent to some category of sets. What do you think? Which category of sets are we talking about? It's equivalent to a subcategory of sets. So the group axioms in particular demand that a group should be
Non-empty.
sorry
Non-empty.
yes. So what do you think now? So this C should be equivalent to the
Set of non-empty sets.
yes. So our claim should be
The
this.
category of non-empty sets.
Yes. So claim is this, that C is equivalent to the subcategory of set whose objects that particular subcategory whose objects are non-empty sets. You have studied about full and faithful functors as well, right, this week? When is a functor full? When is a functor faithful?
Yes.
So you know what a full subcategory is, right? A full subcategory is one in which the inclusion functor is full. That is, in other words, it's a subcategory obtained by taking some objects of your category and taking all arrows between them which existed in the bigger category.
Got it.
So we claim that C is equivalent to the full subcategory of set whose objects are non-empty sets. So let's call this subcategory. Sorry, let's call this subcategory set non-empty. Let's denote it like this. So we want to establish an equivalence from C to set non-empty. So you take C and you take set non-empty. By the way, probably you have learned about an equivalence of categories as a pair of functors going in opposite directions whose compositions are naturally isomorphic to identity functors. And one of the functors is called a part of an equivalence of categories. We'll refer to each functor as an equivalence of categories. Just a small change in terminology. I mean, it really doesn't matter that much, but we'll call this functor to be an equivalence of categories. And any weak inverse or quasi inverse that it has to also be an equivalence of categories. Yeah, so we want to establish an equivalence of categories. So first of all, we want to establish a functor from C to non-empty sets. What should this functor do to objects?
Send them to the same objects.
You shouldn't say same objects, to the underlying set, right?
Right.
This is the forgetful functor, that's all. So sending any group G, because C, the category C has objects as groups. So objects in particular are sets here. In this special case, they are sets with group structure. So G is being sent to underlying set of G. And what does it do to an arrow? So if H is another object sent to underlying set of H, what does it do to an arrow?
Sends it to itself.
Sends it to itself. Because F is an arrow in C, so F is just a set map. It is being sent to itself, which exists in the category of as an arrow in the category of non-empty sets. Okay, so what do you need to show in order to show that F is an equivalence of categories? By the way, you can check that this is a functor. Check that this construction F is a functor. Simple, pretty easy. Yeah, so what do we need to show that F is this functor F is an equivalence of categories?
That there exists a natural isomorphism between one C and F.
So first of all, there should exist a functor in the opposite direction G together with natural isomorphisms, 1 to G composed F and F composed G to 1 on set non-empty. But there is also an equivalent criteria, right? There is also an equivalent way of saying that the functor F is an equivalence of categories. You saw that, right? I'm pretty sure because it's in one of the assignment problems.
No, I'm not sure.
Sorry, can you be a little bit louder?
No, I'm not sure.
You remember the equivalent criteria, right?
No.
Okay, so did you not see that if a functor F is an equivalence of categories if and only if it is full, faithful and... Did you not see this?
No.
Someone else...
Yet to see that.
Oh, yet to see that. Yeah, so can someone else confirm if they have if that condition or that property was being taught? Okay, let me just check one thing quickly.
Okay, it's in the lecture notes.
It's in the lectures, right?
Yes.
Yeah, so Okay, fine. Then we can use it. So this is something that if you are not sure, but you should go and check. Um, so a functor is part of an equivalence of categories in the terminology of your lectures. So is part of, I'll just call it an equivalence of categories, is an equivalence of categories if it is fully faithful, by which I mean that the local maps which are associated to the functor, that is the maps at the level of Hom sets associated to the functor, are first of all injective. That is what the definition of a functor being faithful is. They are surjective, but that is what a full functor means, and hence they are bijective. That is what fully faithful means. And the functor should also be an equivalence of categories. I mean, sorry, and essentially surjective. Yeah. So a functor is an equivalence of categories if and only if it is full, faithful, and essentially surjective. What do I mean by essentially surjective functor? What do you think? So F is a functor. Let's say H is a functor from a category C to a category D. What does it mean to say that H is essentially surjective? And we are talking about essential surjectivity on objects. What do you think essential surjectivity is on objects?
So for any object of D,
Yeah.
there is an object in C such that HC is isomorphic to D.
Exactly. So if H is a functor from C to D, in particular, I mean the part of the data of the functor H is that H, I mean there is a function, let's say H0 from the set, from the class of objects of C into the class of objects of D, right? Now this function might not be surjective itself, but it essentially reaches out to all objects of D. That is what essential surjectivity is, right? And as you said, essential surjectivity is, in precise terms, is that for every object D in D, there exists some object C in C such that H of C, even though it might not be strictly equal to D, is isomorphic to D. So this is the right kind of notion of surjectivity in the context of categories. Again, because you don't want to compare, because you don't want to say that two elements are, I mean, two objects are strictly equal. Rather, you want them to be isomorphic. Right notion of sameness is this. Okay. So keeping that in mind, we are going to use this criteria to show that our functor F is an equivalence of categories. So what are the local maps associated to the functor? So fix objects, let's say A and B, in your category C, in the first category C, in the domain category C. So for objects A and B in C, by definition there exists a map, by definition, of a functor of sets. This is a map of sets from the Hom set CAB to the Hom set set non-empty FA comma FB, right? We'll write this map as FAB for the objects A and B. This is just a part of the data of your functor. And what does this map actually do? It sends every arrow F to, that is, how did we exactly define its action on arrows? What does the functor do to an arrow F? Sends it to itself, right? So this is what it does, sending F to itself. Now tell me, is this map bijective? Is this map bijective? Is this injective, first of all? Someone quickly, is this injective? Are two distinct elements of the domain getting mapped to distinct elements of the codomain? This is injective, right? So the map FAB is injective, and it is at the same time surjective as well, right? Because any arrow in the codomain from FA to FB is just a set map which also exists in the domain from the group A to the group B, because the category C has as its arrows all set maps, right? So FAB is injective and surjective, hence it's bijective. So this happens for every ordered pair AB of objects in your category C. So the functor F is fully faithful. Right? And is it essentially surjective? This is the interesting part of the problem. Is your functor F essentially surjective? In other words, what do you need to show to claim that this functor is essentially surjective or not? Someone answer. I mean, I don't really like classes like this in which people don't interact. I mean, you should and you can. Even if it's wrong, you should interact. Someone tell me, what do you need to show to claim that F is essentially surjective? You need to show that given any set in your codomain, there exists an object in your domain whose image under F is isomorphic to that set, right? So we want to show that our functor F from C to the category of non-empty sets and set maps is essentially surjective. So what do we want to show? What exactly do we want to show? So given an object in your codomain, non-empty sets, which is just a set, non-empty set. So given a non-empty set X in your codomain category, there exists a group G in C such that, because the category C, if you recall, is just the category of groups and all set maps. So such that F of G is isomorphic to X in set non-empty. By the way, in the category of non-empty sets, what is exactly an isomorphism? In the category of sets, we know that an isomorphism is a bijection of sets. And what happens to the category of non-empty sets? What should an isomorphism be? So an isomorphism in the category of non-empty sets should be an arrow that is just a set map together with, I mean, this is the definition of an abstract isomorphism in any category, right? So it should be an arrow which is invertible together with another arrow G in the opposite direction, which composes with F to give you identities on the respective objects, right? And that's just the notion of a bijection even in this category. So an isomorphism in the category of non-empty sets is still a bijection. So what I want is this set Fg should be in bijective correspondence with the set X. Now what was Fg? What was our definition of the functor? What does the functor F do to objects? It sends every group to the underlying set, right? So Fg is just the underlying set of G. So what I want is, given any non-empty set X, we want a group G whose underlying set is isomorphic to X. This is just equivalent to producing a group structure on the set X. That's all, right? We should take our group G to be X together with some binary operation, so that if F is applied to this object, this group, its underlying set is just X, and X is isomorphic to X in bijective correspondence with X, right? So the entire problem just boils down to this question: can any non-empty set be endowed with a group structure? Given any non-empty set, can you produce a binary operation on it which makes it into a group? What do you think? Suppose your set is finite, it has n elements. Can you produce a binary operation on a set with n elements to make it into a group?
Just Zn.
Yes, correct. Zn. So basically, absolutely correct. So good. So take any set X with n elements. Now this, there is a bijection from X to Zn as sets, right? And you can use this bijection to induce a group structure on X. So let's call this bijection F. Then given two elements of X, so let's say A and B in X, you want to define your binary operation. So A, you define A star B to be equal to F inverse of Fa plus Fb. So what you are doing is, you have A and B in X, looking at their images Fa and Fb in Zn. Zn, the codomain here, has a group structure. You can make sense of addition Fa plus Fb. Now this is another element of Zn, and you look at its inverse image, right? You look at that particular element Y in X, which gets mapped to Fa plus Fb, and you declare A star B to be exactly equal to Y. And you can check that this induces a or defines a group structure on X in such a way that F also becomes an isomorphism of groups, not just an isomorphism of sets, right? So for finite sets the problem is easy, but for any arbitrary set, this is the answer to this is again in the affirmative, and this uses the axiom of choice. So we won't get into the details of this. I'll just give you a small argument. Please go back and check this out. Check the details of this argument. By the way, are you guys aware of the axiom of choice? Axiom of choice basically says that given any non-empty collection of sets, given any collection of non-empty sets, you can always pick one element from each member of the collection, from each set in that collection. Intuitively, it seems to be very obvious, but it isn't, because you don't have an algorithm to pick elements, right? So there is no guarantee that you will sort of pick elements from every set involved in the collection, right? So that is why this needs to be called an axiom. It can neither be proved nor be disproved using the usual laws of mathematics or usual ZF axioms in mathematics that that you use. So that is why you need this axiom of choice, and the axiom of choice basically says that this is true. It implies that every set can be endowed with a group structure, and not only so, the converse of this statement is also true. That is, if every set can be endowed with a group structure, then the axiom of choice is true. But yeah, we won't get into so much details. We'll just write down an argument for this. So X is your set, right? What you do is you take this particular group, direct sum of copies of Z indexed over X. So direct sum of X copies of Z. So if X has two elements, this this group is just Z direct sum Z. If X has three elements, this group is Z direct sum Z direct sum Z. So you are taking direct sum of X copies of Z, and the interesting thing is, using the axiom of choice, you can prove, using AC, the axiom of choice, you can prove that the cardinality of this set is exactly equal to the cardinality of X. Because the direct sum, so the intuitive idea is this, that the direct sum of X copies of Z is just the collection of finite subsets of X cross Z. So we don't have please go and verify this yourselves. If you have any questions, we can deal with that, but for now we'll just say that the cardinality of the direct sum of X copies of Z is exactly the cardinality of X, because the direct sum of X copies of Z can be thought of as finite subsets of X cross Z. So if you take this finite subset, let's say x1 comma 1 and x2 comma let's say minus 5, if this is your finite subset of X cross Z, then the corresponding element in the direct sum that we are talking about is this. So in the x1 component you have 1, rest of them are 0, and in the x2 component you have minus 5, everything else is 0, right? So elements, so there is a bijection from finite subsets of from the set of finite subsets of X cross Z to the direct sum of X copies of Z. And since, and again using the axiom of choice, if X is infinite, the set of finite subsets of X cross Z has the same cardinality as X cross Z. And again using the axiom of choice once more, the cardinality of X cross Z is exactly equal to the cardinality of X. Okay, so everything is happening in the, so assume X is infinite, so everything is happening for the infinite case, infinite cardinality case. If X is an infinite set, then the cardinality of this set is equal to the cardinality of this set. So again you have a bijection X to the direct sum of X copies of Z. This is already a group, this is already a group, right? We use the bijection as we described just before. We use this bijection to induce, so use this bijection to induce a group structure on X. That's all. Please go and have a look at this axiom of choice argument, to show that every non-empty set can be endowed with a group structure. If you have any questions, we'll answer this in the next week. Okay. So this sort of answers our entire question. So first of all, we have seen that every set can be endowed with a group structure. We don't care what that group structure actually is. We just want this fact to be true, that every non-empty set can be endowed with a group structure. And now this also solves our problem as well. So the functor f is essentially surjective, because you start with any non-empty set X in your codomain, right? You want to produce an object in your domain whose image under f is isomorphic to X, right? That is, you want to obtain a group in your domain whose image under f, that is, whose underlying set of elements is in bijection with X. So better to just take X itself and put a group structure on it. The axiom of choice guarantees that every non-empty set has a group structure. So you take that particular group X with its binary operation. This gets mapped onto X, and X is of course isomorphic to X, right? And that solves the problem entirely. So so what we essentially proved is this, that f is essentially surjective. So f from C to the category of non-empty sets is an equivalence of categories. And therefore, since the functor f is an equivalence of categories, we are done. So no point in considering the category C. See, that is no point in considering the category of groups together with set maps as its arrows, because that category is equivalent to the category of non-empty sets, which we already know about. And that is why you should always, whenever you consider a new type of mathematical object, the right notion of arrow should be a structure preserving arrow, because otherwise you might land up into something which you already know about. That is the point of this conceptual problem. That's all. If you have any questions, please feel free to ask me. Okay, so let's come to this. So you take two categories A and B. You need to prove that the functor category from A op to B op is isomorphic to the functor category, to the opposite of the functor category from A to B. But first of all, tell me, do you know what a functor category is? What is a functor category? So given two categories C and D, what is the functor category from C to D? Anyone?
Objects are functors and morphisms are natural transformations.
Exactly. So as I mentioned, functors should be treated as mathematical objects in their own right, and there is a notion of a map in the context of functors which is called a natural transformation. So it's natural to expect that the functors should themselves form a category whose arrows are the natural transformations, and that is exactly the data of a functor category. So the functor category from C to D, written in this particular way as you can see here, is a category whose objects are functors from C to D and whose arrows are natural transformations from one functor to another functor. Right. So this question starts with two categories A and B. So you know about opposite categories, right? It's the opposite category of a given category. So given a category A, you can obtain its opposite category A op. Similarly, given the category B, you can consider the opposite category B op. Now A op and B op are categories themselves, so you can ask about the functor category from A op to B op. This is your first category. And you can yourself ask about the functor category from A to B, because A and B are categories. So this is again a category, and you look at its opposite category. So this is your second category. What the question is asking about is to establish an isomorphism from the first category to the second category. So what is an isomorphism of categories? We already mentioned this, but if you just look at the category whose objects are categories and whose arrows are functors, an isomorphism in this category is exactly what an isomorphism of categories is, right? So basically, what is an isomorphism in any arbitrary category C? Given a category C, an isomorphism is an arrow A to B such that is for which there exists another arrow GB to A. There exists an arrow GB to A such that G composed F is 1A and F composed G is 1B. This is exactly the definition of an isomorphism in an abstract category. This definition, if specialized to the category cat, means that there should exist a functor from your category A to from your category A to your category B, together with a functor in the opposite direction, such that these two functors compose to give you identity functors on the respective categories. So what you want here essentially is a functor from the category, from the functor category from A op to B op to the category, to this category, the opposite of the functor category from A to B, and you want this functor to be an isomorphism, by which we mean there should exist a functor in the opposite direction such that G composed with F is identity on this category and F composed G is identity on this category. This is all that you want. So the first step should be to come up with a functor F from the first category to the second category. So first step is to come up with a functor F from this category to this category. Then we'll construct a functor in the opposite direction. Yeah. So what should this functor be? What do you think? Let's call this functor omega, by the way, because we'll use f, g, h for functors between a and b, or their dual or their opposites, etc. So let's call this functor omega, let's say. So we need to produce a functor omega from this category to this category. Question is, what should this functor be, or what should this functor do? So take any arbitrary functor h here, which is an object in this category. Where should h be mapped to? So keep in mind, h is a functor from what to what? It's a functor from h op to b op. This is what an object in your domain category is. A functor h from a op to b op. What we want is an object in the opposite category of a comma b, right? We want an object in the opposite category of a comma b. So tell me, what was the opposite category again of a given category? Given a category C, the opposite category C op has as objects the same objects as that of C, just the arrows in C op are flipped, reversed, right? They are in the reverse direction. That's all that is there in the definition of the opposite category, right? So if C is a category, the category C op has the same objects as the category C. The arrows of the category C op are flipped, are in the opposite direction. So if there is an arrow A to B in C, F, then we'll have a corresponding arrow F op, B op to A op, B to A in C op. That is what the opposite category exactly is, right? And compositions should change accordingly. This is the construction of the definition of the opposite category. So given a category C, C op is another category with the same objects as C, but with the arrows of C flipped or reversed in the opposite direction. To avoid any kind of confusion, we'll call the arrows of C by simple letters F, G, H and so on, and we'll call arrows of, or denote arrows of C op, the corresponding arrows of C op, by F op, G op and so on. Those arrows are in the opposite direction as that of the original arrows F. That's all. So since the opposite category has the same objects as that of C, so the objects of this category A comma B op are exactly the same as objects of A comma B. So the objects of this category are exactly functors from A to B. So what I want is a functor from A to B, given a functor from A op to B op. This is what should be here. So yeah, so tell me, given a functor h from A op to B op, I want to produce a functor from A to B. What functor should I take? Or what functor should we take? are the lectures, is this getting complicated or is this okay? At least confirm that. I mean, are you guys okay with the explanation so far? Okay. Just feel free to stop me anytime and please do speak up. I want this session to be interactive. Yeah. So H is a functor from A up to B up. I want a functor from A to B.
You can take a functor that maps objects of A to H of A
Okay.
and morphisms, let's say F in A to H of F op.
Correct. Absolutely correct. So H was your functor from A up to B up. I'll denote my functor by H1, even though this is not exactly the correct notation for this. There is also notation for this as well. But let's for the time being denote this by H hat. I want this functor H hat from A to B. So given an object A in A. Now if A is an object in A, we know that opposite categories have the same objects as the original categories. So both A up and A have the same objects. So if A is an object in A is also an object in A up. So it makes sense to apply H on A, right? So I have an object H of A, which is an object in B up. And again, B up and B by our convention has the same objects. So if HA is an object in B up, HA is also an object in B. So it makes perfect sense to have the object HA here. HA is an object in B, and what my H hat does is maps A to HA. This is what it does to the objects. And what does it do to the arrows? So B gets mapped, let's write A prime. A prime object gets mapped to H of A prime. And what happens to an arrow F? So F is an arrow in the category A from A to A prime. I want to map this to an arrow from HA to HA prime, right? That's all that I want. I need to find out what particular arrow from HA to HA prime is there in B, to which this arrow F can be mapped onto. Right? Pretty simple so far. So F is an arrow A to A prime in A. Right? Look at the opposite category A up. What did we say or what did we mention? The opposite category is just a formal construction, right? The objects are kept the same, just the direction of the arrows are reversed, right? The arrows are just flipped. That's all the opposite category is. So the arrows of the opposite category are in bijection with the arrows of the original category, just the direction of the arrows are flipped. So if A to A prime, F is an arrow in the category A, then there is a corresponding arrow A prime to A, which will write by F up in the opposite category A up, right? So F up is an arrow A prime to A in the opposite category A up. Now look at the functor H. H is a functor from A up to B up, right? So it can be applied on arrows of A up. So H in particular can be applied on the arrow F up in A up. What is the direction of this arrow? This is the direction of this arrow is from HA prime to HA, and this is an arrow in B up, because H was a functor from A up to B up, right? So given your arrow F up from A prime to A in A up, H of F up is an arrow HA prime to HA in B up. That's all. But we can't stop here exactly, because we need to land to an arrow in B, and we have landed to an arrow in B up, right? So just look at the corresponding arrow in B, corresponding to this arrow in B up. Just look at the corresponding arrow in B. So the corresponding arrow, which is F H of F up of op, is an arrow from HA into HA prime, right? In the opposite direction. This is the corresponding arrow in B, right? So that is what our arrow is. HA to HA prime, H of F up op. That's all. So I'll just quickly write this down in brackets so that you guys can understand. So F is an arrow A to A prime in A implies there exists an arrow, the corresponding arrow a prime to a if op in a op, which implies the which implies that you have an arrow, uh, you have an arrow from h a prime to h a, because h was a functor from a op to b op, h of f op in b, sorry, b op, because h is a functor from a op to b op, which implies that you have an arrow h a prime, I mean sorry, you have an arrow h a to h a prime in the opposite direction. H of f op was your arrow in b op, you are taking the corresponding arrow in b, so apply an op on top of that, so this is an arrow in b. So this is what your functor h hat does, sends any arrow f to h of f op of op. Okay, right, so this is your h hat, and you can check that h hat is a functor because h was a functor, you can check that h hat is a functor. That is, it preserves composition and identities. It already preserves domain and codomain operations. You can check that it also preserves composition and identities. So check that h hat is a functor. So we'll send h to h hat. Right. Okay, let's add a page. So let's just quickly recall what have we achieved so far. Oops. We have achieved this functor omega from the domain category to the codomain category, sending any h to h hat, where h hat has this description, right, so far. So we are omega should be a functor, so we should also map arrows to arrows. It should also act on arrows, send them to arrows. So it sends h to h hat, let's say it sends g to g hat, where g hat is defined in exactly the same way as h hat was defined. What does it do to an arrow? So what is an arrow in your category? It's a natural transformation alpha, right? Where should alpha be mapped onto? We'll call this alpha hat. Yeah, so where should alpha be mapped onto? So alpha is a natural transformation from the functor h to the functor g, right? H and g are functors from a op to b op. You want a natural transformation from h hat to g hat, where h hat and g hat are defined in exactly this way. They send objects a to h, they send arrows f to h f op of op. I mean they send arrows f to h of f of op. Yeah, so what natural transformation should you have? Alpha hat from h hat to g hat. What is the data of a natural transformation exactly? The data is exactly that alpha hat, I mean a natural transformation is exactly an arrow, right? I mean a natural transformation is exactly a map, right, that assigns to every object of your domain category some arrow in the codomain category, and this data is subject to the naturality axiom, that is, you demand certain squares to commute. So let's just focus on the data. So alpha hat is exactly a map, that is, you can also think of it as a collection of arrows from h hat of a to g hat of a, alpha hat a, where a is an object in your domain category which is the common domain category of the functors h hat and g hat. What is that? H hat is a functor from A to B. G hat is also a functor from A to B. So A should be an object in A. Yeah. So you want to define a family of arrows alpha hat A from H hat A to G hat A. What is H hat of A? This is just H of A by our very definition of the functor H hat sends every object to H of A. So from HA to GA you should have arrow. You should have an arrow. Keep in mind that we want these arrows to be in script B because H hat and G hat are functors from script A to script B. But so far we already have alpha as an natural transformation from H to G. So when H and G are just functors from A up to B up, right? See, I cannot just take alpha at A, right? I cannot just take alpha at A because alpha at A would be an arrow in B op. I want an arrow in B. So there is some issue. What is that? There is some problem, some issue. What is that? What is the issue? The issue is the op. We completely ignored the op here, right? We want a functor into the opposite category of A comma B, and a functor into the opposite category of A comma B should map arrows from your domain category to arrows in the opposite category of A comma B, right? So alpha hat, the arrow which we want from H hat to G hat, should be an arrow in the opposite category of A comma B, right? So it doesn't mean that it's a natural transformation. It's just a formal, the construction of the opposite is just a formal construction in which you flip the arrows, right? That's all that you do. So what you want should be an arrow. I mean, you want an arrow alpha hat from H hat to G hat, but this arrow should be in the opposite category. So you need to come up with an arrow in the original category A comma B, and then you can just consider the corresponding arrow, flipped arrow. That's all. Okay, so what we should really want, so let's call it alpha hat. But keep in mind, alpha hat is not a natural transformation. That is what I am trying to say here. It's just an arrow which corresponds to a natural transformation, right? In the opposite category. So we'll come to this, but for right now let's stick to the definitions. We'll come to this in a while. Right now let's just stick to the definitions, and let's just try to produce an arrow alpha hat from H hat to G hat in the opposite category. That is, let's try to produce an arrow G hat to H hat in the category A comma B. An arrow in the functor category A comma B is a natural transformation. So what we should really be asking about is a natural transformation from G hat to H hat in the functor category A comma B. That's all. So what I'm trying to say here is this. So you are given a natural transformation alpha from the functor H to the functor G. So let's write the full domain and codomain just to be exactly clear about all these things. So you have A up, you have B up. H is a functor from A up to B up. G is a functor from A up to B up. You have a natural transformation alpha from H to G. What is the data of this natural transformation? Alpha is exactly equal to a family of maps from HA to GA. These maps are in B op. Let's call this map for the given object A in A op, the domain category. Let's call this map to be alpha at A. This is how you write the components of a natural transformation. So alpha at A is a map in B op. Keep that in mind, from HA to GA. What I want is this. I want a natural transformation from G hat to H hat. I want a natural transformation from G hat to H hat in the category A comma B. so that this arrow, this is an arrow in this functor category. If I want an arrow in the opposite category, I can just flip it, right? So I just, for now I want an arrow in the functor category A comma B. An arrow in the functor category A comma B is by definition a natural transformation. So what I want is a natural transformation from G hat to H hat. That's all that I want. So tell me, what natural transformation? In other words, what is that particular family of arrows that I should take? So let's write this in full. A is your category, B is your category, G hat is your functor from A to B, H hat is your functor from A to B, and you want a natural transformation from G hat to H hat. So you want exactly a function which assigns to every object of A some arrow in B, subject to naturality axiom. And a function can be equivalently be thought of as a family. So you want a family of arrows from G hat of A to H hat of A. One with exactly one arrow with exactly one map for every object A in A. All these arrows should be in B. What should we take these arrows to be? You are given this data. You want something here.
You can take the collection of alpha A ops.
Exactly. So keep in mind, how was G hat A and H hat A defined? G hat A was GA, H hat A was HA. So I wish I had some more space to write this, but let's see. Oops. This is G hat A, this is H hat A. Now G hat A was just GA by definition, H hat A was just HA by definition. You want arrows in B. You have arrows from HA to GA in B op. So just take alpha A op. Exactly. Check that since alpha A or since alpha is a natural transformation, by which I mean that this arrows alpha A are natural in the variable A. That is, in other words, the naturality axiom holds. So if you start with any arrow in A op, you should get a square in B op, and you want that square to commute. That is what the naturality axiom says, right? It loosely speaking, what does the naturality axiom do? It sort of captures the idea that this alpha A maps for every object A. This map alpha A is defined in exactly the same way. It's defined in a uniform way across all objects of A of your category A op, right? You don't have one definition of the map alpha A for a particular object A in A op, and you don't have another definition for, let's say, an object A prime. I mean, you don't have another definition of alpha A prime for an object A prime. The maps alpha are defined in exactly the same way, right? Roughly speaking, this is what intuitively the naturality axiom captures. This is the idea of the naturality axiom. You have many times, I'm pretty sure you have many times in mathematics seen terms like something is canonical, or let's say there is a canonical isomorphism or a natural isomorphism from a vector space, finite dimensional vector space, to its double, dual, etc., etc. So naturality exactly means this, that regardless of what vector space you pick, you always define that map in exactly the same way. So since alpha is a natural transformation, check that. Please do check this. These are short exercises for you. Check that alpha hat, we didn't have a name for this. What should we write? Alpha prime, let's say. Yeah. Check that alpha prime is also a natural transformation, or check that alpha A op is natural in the variable A. That is, alpha prime is itself a natural transformation. So what you need to verify is exactly this, that given any arrow in the domain category A. So what you need to verify is, given any arrow in the domain category A, let's say A to A prime F, you of course will get a square in the codomain category B. What is your square? Your square will exactly be this. So G hat A to H hat A, you have alpha A op, and G hat A prime to H hat A prime, you have alpha at A prime op. These components will form a square. So from GA to GA prime you have G hat F, and from H hat A to H hat A prime you have H hat of F. Right? You want this square to commute. This is what the naturality axiom says. This square should commute. So check that this indeed happens for any arrow F A to A prime, for any arrow F in the category A. This is what naturality means, right? And this will exactly be the consequence of the naturality of alpha. So check that alpha prime is indeed natural. Is a natural transformation. Right. So we have a natural transformation from G hat to H hat in the functor category A comma B. What we want is an arrow from H hat to G hat in the opposite category. So just take the corresponding arrow, that's all. So oops, God, yeah. So we define this to be, so we have alpha prime in the functor category A to B from G hat to H hat. We want this, we define this arrow to be alpha prime op in the opposite category A comma B op. That's all. Again, there are certain number of things that you need to verify. Verify that, so omega has, as a functor, has been defined on objects, and we show that this construction is functorial in the sense that it also extends to arrows of the category, right? So any arrow alpha gets mapped to alpha prime op, where alpha prime is exactly defined in this way, as we have done here. This is your alpha prime. So the next thing that you should check is omega is indeed a functor, in the sense that it preserves compositions and identities. We have already shown that it preserves domain and codomain. You show that it preserves composition and identities. So given another functor T, let's say, and you take an arrow beta, that is a natural transformation beta. So beta gets mapped to beta prime op, and T gets mapped to T hat. And what you check is that this composition, if you take, is exactly the image of this composition. Okay, that is what you need to check in order to verify that this is a functor, and check that it also preserves identity natural transformations. So I'll again leave this as a short exercise. Check that omega as defined above is a functor. Right. But we can't end here, right? We should also discuss about the existence of another potential functor in the opposite direction. Because we want to establish an isomorphism of categories, we claim that omega is indeed itself an isomorphism of categories. So the functor omega should have an inverse functor, right? So I'll just leave it here with a small question, or rather with a small hint of how to obtain the other functor. So you guys will tell me this. So what about the opposite direction functor? What about a functor? So what is another Greek letter? Theta, let's say. Theta. What about a functor theta in the opposite direction from A comma B op to A op comma B op? What about this functor? What about this functor? So if you take an object H here, which is just an object in the category A comma B, because dual categories or opposite categories have the same objects. So if H is a functor from A to B, you want to construct a functor from A up to B up. What functor should you take? We write it as H up. H up should be a functor from A up to B up. What is your H up functor? It should send an object A to HA, because again of the same reasons, because A is an object in A of, A is an object in A, H can be applied on A to get an object in B, HA is an object in B, B up and B has the same object, so HA is an object in B up. This is what it does to objects, sends the object A prime to HA prime. And what does it do to an arrow? So if F up is an arrow from A to A prime in A up, that means that F is an arrow A prime to A in A, H can be applied on this to give an arrow HF from A prime, HA prime to HA in let's write this, yeah. So you start with an arrow F up, A to A prime in A up. You want to define the action of H up on F up, right? So F up is an arrow here, implies that F is an arrow A prime to A in A. H can be applied on this because H is a functor from A to B. So H of F is an arrow from H of A prime to H of A in B, which implies that H of F op is an arrow from H of A to H of A prime in B op. Pretty simple. So just map F up to HF op. That's all. Okay. I don't know if this is clearly written. Yeah. So H of F op. Yeah. Check that this H op is indeed a functor. It will be a functor. And how do you define on natural transformations? In exactly the same way. Let's not discuss that. If you have any questions, again, feel free to ask me in the next week, or email me, or put up a question in the discussion forum. Okay, but the idea is exactly the same. Finally, you check after you define the action of this functor, check the functoriality of the functor, and finally you check that these two functors are exactly inverses of each other. That is, omega and theta will be inverses of each other. Omega composed with theta will give you the identity on A comma B op, and theta composed with omega will give you the identity on A op comma B op. Okay. So yeah, we get to the next exercise. Let's take a small 2-minute break and let's think about what did we achieve so far. And there's something important that I wish to tell you right now, but this was somewhat a heavy exercise. In fact, this was just only involved symbols and all. There was no actual semantics involved in this, but try to think of what have we achieved. So given categories A and B, we have shown that the functor category from A up to B up is isomorphic as a category to the opposite of the functor category from A to B. That is what we achieved. In other words, op, when applied to this bracket, distributes over the members of the bracket, the entries of the bracket. That is what we have achieved. It's entirely simple and straightforward. It seems like we have written a lot, but we actually didn't do anything. This is just using the definition. But the important thing that I want to stress here, so that you guys don't get ever confused, is this, and keep this in mind please. So if C is a category, we know how to construct the category C op, right? It's just a formal construction in the sense that the objects of C, if A, B, C are objects in C, the objects of C op are also the same, A, B, C and so on. The arrows are just reversed. That the direction of the arrows is just reversed, right? They are flipped. So if I mean, if you take an, I mean, the home set in C from A to B is written CAB, and what do you define the home set in C of from A to B? This is exactly defined to be C of B comma A, right? That is what I mean, right? That is, in other words, if so, let's, yeah, C B comma A is a home set in C. The home set from A to B in C of is exactly C B comma A. In other words, if F is an arrow in C from B to A, then the corresponding arrow in C op is written as F op from A to B, right? I mean, this notation suggests that this should be equal. So if F is an arrow B to A in C, then I should write the corresponding arrow as F itself from A to B. But just to avoid confusion, what we do generally is, this is the convention, that arrows in C are written by simple letters F, G, H and so on, and arrows in C op are written by those letters supplied with an op as your at the top. So if F is an arrow from B to A in C, we write the corresponding arrow from A to B in C op by F op. Okay. Now what I want to stress here is something very important, which is this, that this is just a formal construction, as I just mentioned. What you are essentially doing is just flipping the arrows and looking at the corresponding category. That will give you a new category with its own composition, identity, etc. The point is that this is a category theoretic construction, and never mess it up with sets. Okay, so what I in particular mean is that if you take the category of sets, so if C is equal to set, then you know that its objects are sets A, B, C and so on, and an arrow from an object B to an object A, that is from a set B to a set A, is taken to be a set function, right? Now if you look at this opposite category set op, so this is a function, right? If you look at the opposite category set op, it has the same objects A, B, C, sets, these are objects, but you treat them as objects, right? In fact, in any category you treat the objects as primitive notions, as basic notions. There is no internal structure supplied to them. So think of A as a letter, think of the set B as a letter, think of the set C as a letter, think of them as dots, let's say 3 dots. This is dot A, dot B, dot C, or think of them as blobs, whatever you want. Just think of them as objects, and an arrow from object A to object B is just to be thought of as an arrow. Never mix it up to be a function. This is not a function, okay? So if F was your original arrow in the category of sets, you write the corresponding arrow as F op from A to B in the category set op. Even though the objects A and B are sets here, this doesn't mean that F op should be a function. F op is just a symbol, just a formal arrow. That's all. And it turns out that you cannot think of F op as a function, in the sense that the category of sets and its opposite category are not equivalent. They are different categories. So F op is just an arrow. Okay. In the same sense, or in the same way, this is something that we stumbled upon right now, or observe something right now. We had this functor category A comma B. We had this functor category, opposite functor category A comma B op. The objects are functors F, G, H and so on. We write the corresponding functors like F, G, H and so on in the opposite category. An arrow in this category A to B is just a natural transformation from, let's say, G to H, alpha. There is of course a corresponding arrow in the opposite category from H to G, which we'll write as alpha op, but never mess it up or never think that this alpha op is a natural transformation. Okay, even though H and G are functors here, alpha op is just meant to be thought of as a simple arrow. Think of H as a blob, forget that it was a functor, just think of it as a mathematical object. Think of G as a blob, a mathematical object, and alpha op is just a formal arrow from H to G. That's all. This is not a functor, this is not a natural transformation. You can't think of this, because the construction of the opposite category is only a construction involving categories, And in categories, you think of arrows as symbols, as mere symbols, nothing more than that. I mean, sometimes in specific examples of categories, you take this arrow to be, let's say, a function, you take this arrow to be a group homomorphism, but you should think, whenever you are a category theorist, or whenever you are thinking like a category theorist, you should think of the arrows exactly as arrows, as mere symbols. And that is what is and that is what the opposite category construction does. Think of the corresponding arrows in the opposite category simply as arrows, just as you think of the arrows in the original category simply as arrows, not anything more than that. Okay, and that is all that I wanted to stress. By the way, is this clear or did I confuse? Please someone confirm. Maybe Nisar can confirm, because you are the only one who's speaking up.
I'll need to think about it.
Okay, Advay, was this clear?
Yes, sir, it's clear.
Yeah. So what I want to say is, just think of this natural transformation as this arrow in the functor category, and think of the corresponding arrow alpha op in the opposite category again simply as an arrow. You should never think of it as a natural transformation. It is not a natural transformation at all. It is just a symbol. Okay. Many times people do have a, I mean, if you are taking an arrow in the opposite direction, you tend to think of it as a function or as a natural transformation or as a functor maybe, but that's wrong. You shouldn't. It's not a functor, or not, it's not a natural transformation, it's not a function. These are concepts in particular theories. I mean, for example, a function is a concept in the in the specific category of sets, and nowhere is it mentioned, or nowhere did I say that set op should be the category of sets. It's something entirely different than the category of sets. As a category, it's just an abstract category, so the arrows are just abstract arrows. Don't think of them as functions. That's wrong. Just these are just arrows, because this is what the opposite construction is all about. It's a category theoretic construction, it's a formal construction. You just flip the direction of the arrows. So those are just arrows that you create in your opposite category. Okay, there is nothing more to them. So I'll write it here. Caution. Caution. Just arrows. Always it's better to think of arrows as arrows. Okay, I mean, you can take particular examples, for example the category of sets, even though, I mean, the definition of an arrow in the category of sets is that it's a function, but you should still think of it formally as just an arrow in the category of sets. Okay, if you are saying that this arrow is a function, that means you are in particular diving into set theory. You are using set theory. But as a category theory person, you should say that, or if you are thinking category theoretically, you should say that this function is an arrow in the category of sets. So think of the notions, I mean, keep a safe gap between the two notions. Don't mix them up. One is a set theoretic notion, one is a category theoretic notion. Yeah, so spoke a lot. Let's quickly solve, at least try to solve one or two more problems. Let's solve the easier one first. We'll come to this one. Okay, very simple, very let's do it quickly. So for a mapping F from T to S of sets, the following identity holds. This is your identity. We know this to be true, right? We have seen this in set theory previously many times. What does it say? So if F from T to S is a set map, then T minus F inverse A is F inverse of S minus A for all subsets A of S. And this is pretty easy to prove. How do you show this? So x is an element in T minus f inverse of A for some subset A of S, will imply that x is not in f inverse A. It's in T but not in f inverse A. So let me write. So f is a map from T to S. You pick a subset A of S. You can look at the subset f inverse A, the pullback subset, or the what is it also called, the inverse image subset. So x is in T minus f inverse A implies that x is not in f inverse A, which implies that f of x cannot be in A, because if it were in A then x would be in f inverse A, which implies that f of x is in S minus A in the codomain, which implies that x is in f inverse of S minus A. So T minus f inverse of A is a subset of f inverse of S minus A, and you can flip the arrow. I mean, the implications in the other direction also hold, and hence these two sets are equal, right? So these two sets are equal. This is an identity which we have in set theory. The question is asking you to translate this statement in the language of the contravariant power set functor. So I'm pretty sure you have seen the contravariant power set functor this week, and let's just quickly recall its definition. So the contravariant power set functor f from set op, let's write it as let's write it like this, 2 power gap. Okay, because for any set A, the power set of A is sometimes written as 2 to the power A, right? The set of maps from A to 2 element set. So we'll write it as 2 power gap. So this is a functor from set op to set, which sends any set A to the power set of A, 2 to the power A. That is a collection of all subsets of A. And because it's contravariant, we wrote an op in the domain, right? Because it's supposed to flip the direction of arrows. I mean, if I wrote it as a functor from set to set, I mean, I could have also written it as an arrow from set to set, but keeping in mind that it always flips the direction of the arrows. So if there is a function A to B, there is an arrow A to B in set, that is a function A to B in set, then the corresponding or the image arrow should be an arrow from 2 to the power B to 2 to the power A, right? That is what the contravariant power set functor does. So it's better to just write an op, and then you can just talk about a functor. In other words, a contravariant functor from C to D is exactly the data of a covariant functor from C op to D, right? That is what we are saying. So yeah, this functor sends A to 2 to the power A, it sends B to 2 to the power B, and what does it do to a arrow f op in set op from A to B? So the domain category is set op, so an arrow in set op will be written as f op for some arrow f in set. Now f op has direction A to B in set op, which implies that f, so let's write it here, which implies that f is an arrow from B to A in set. Now what is the description of an arrow from B to A in set? An arrow in set is exactly a set function, a set map. So f, that is, f is a function or a map, set map from A to B to A, sorry, in set. So you started with an arrow f op in setup. What you therefore have equivalently is a function from B to A in set. It should get this f op arrow should get mapped to an arrow from 2 to the power A to 2 to the power B, right? In set, that is, an arrow in set is a function, so it should get mapped to an arrow that is you want a function from 2 to the power a to 2 to the power b in set. What you are given is an arrow f of from a to b in set of, that is a function f from b to a in set. How do you get this arrow or this function? Let's write it as 2 to the power f. Let's say, yeah. What is this 2 to the power f function? In other words, given a function from b to a, you want to obtain a function from 2 to the power a to 2 to the power b, from the power set of a to the power set of b. What is this function? Take any element in the power set of a subset S of A. Where should you map it to?
F op of S.
Sorry, I didn't get it. What is f op of f?
F op of S.
No, what is... So again we are confusing. F is a function, right? From B to A. F op is just an arrow. It's, as I mentioned previously, f op is to be thought of as simply an arrow, because f op is an arrow in set op, isn't it? You can't think of it as a function. It's wrong. It's not a function. It's just a formal arrow. Category theory only says that f op is just an arrow. So f op cannot be applied to something. F was an arrow in set, and you know that the category of sets has this description that the arrows in sets are exactly functions. So f as an arrow in set can be applied. I mean, f as an, since f is an arrow in set, it's a function. So f can be applied to something. But f op is just a formal arrow. That's all. You cannot apply f op to something. That doesn't make sense.
So Fs op.
Again, what is fs op? So what is, so f applied to s, fine. Even though this is also not correct, but let's for the time being assume that there is something called fs. Fs is a set, right? It's an object. What do you mean by op of an object? That doesn't make sense, right?
Right.
So not fs, but let's think about this. Forget ops for the time being. Forget there is an op or something. This is your question.
F inverse of S.
Yes, this is your question. F is a function from b to a. You want to obtain a function from 2 to the power a to 2 to the power b. So where should a subset S of A be sent to? It should be sent to some subset of B. Which subset should we take? It should be F inverse of S, right? Because F is a function. F is a concrete function, right? From B to A. So this should be sent to F inverse of S. Okay. So this is what your 2 to the power f does. This function sends any subset S, that is any subset S of A, which is, that is an element S of 2 to the power a, to f inverse of S, which is an element of 2 to the power b, that is a subset of B. Because f op is an arrow from A to B in set of, this means that f is an arrow in set from B to A, that is, and we know what an arrow in set is. An arrow in set is exactly a function. So f is a function b to a in set, that is, f is a function b to a in set, and S is a subset of the codomain A. You can just pull it back along f, that is, just take f inverse of S, which is a subset of B, and this is what your 2 to the power f map does. It sends any subset S of A to the subset f inverse S of B. So yeah, you can check that this is a contravariant functor, etc., etc. I mean, you can check that this is a functor from set up to set. That's okay. This is your power set functor that was introduced this week. Now tell me, we want to translate this identity in the language of the power set functor. This identity starts, or rather this statement starts with an arbitrary mapping ft to S. You have this following identity. How do you translate this in the language of the power set functor, or rather in the language of everything that you have learned this week? So we have a functor. We have a power set functor from set up to set. How do you translate this? What do you think? I mean, I understand the question is not very precise right now, but give it a try at least. So the data starts with an arbitrary mapping on an arbitrary arrow in the category of sets. What particular axiom you have seen this week which starts with an arbitrary arrow and then talks about an equality or an equation, or rather a particular diagram to commute? You have seen something this particular week, some definition which starts with an arbitrary arrow, then talks about a square and asks for the commutativity of that square. The definition of a I mean, I understand this is not very precise, but at least give it a try. The
A
definition.
natural transformation.
Exactly. Exactly. So what we want is, so this exactly looks in the shape of having some natural transformation. So what I want is a natural transformation involving the power set functor. We have one functor which is the power set functor. What should that other functor be so that this entire identity can be captured in terms of a natural transformation from that functor to this functor or whatever you want. So T minus F inverse A is F inverse S minus A. So F inverse, this pullback thing, this inverse image thing is applied on both sides of the equation, right? Which suggests that, so where did F inverse appear actually? In the description of the contravariant power set functor, F inverse actually appeared when you wanted to describe the action of the power set functor on an arrow, right? That is where F inverse appeared. Since F inverse is in both sides of this equation, we suspect that the power set functor, we suspect that the natural transformation should be a natural transformation from the power set functor to itself. Let's see. So what I'm claiming is, so you have this power set functor from set op to set. You have the power set functor again from set op to set. What I want is a natural transformation from the power set functor to itself, or an endo-natural transformation of the power set functor. So 2 to the power this, 2 to the power this. I want a natural transformation like this. Let's call it alpha. In such a way that the naturality axiom should exactly mean this statement. So what does this equation in particular talk about? It talks about a set difference, which we haven't considered so far. So it's pretty obvious right now that the definition of the natural transformation alpha should involve some kind of set difference. In other words, what is a natural transformation alpha? We know that it is a map that assigns to every object A of your domain category, which is set op in this case, a unique arrow alpha A in the codomain category set from this functor applied on the object A to this functor applied on the object A. So from 2 to the power A to 2 to the power A, right? This is what alpha A should be, right? So alpha is a map which assigns to every object A of your domain category some arrow in the codomain category from 2 to the power A to 2 to the power A, from the power set of A to the power set of A. So what should this arrow be? In other words, if you take a subset S of A, you want to map it to a subset, to some subset of A. What subset should we take? And keep in mind, we want to incorporate this set difference thing in the picture. Yeah. So where should S be sent to? Just a guess. This should be this problem is supposed to be about an educated guess. That's all. So where should you map this to? You should map it to. So you are taking a. So this is A. This is A. You want. I mean, think about this. You have a set A. You take a subset S of A. You want another subset of A that involves set difference. What should you take? It should be A minus S. Simple, right? A minus S. If S is a subset of A minus S is again a subset of A. So, anyways, let's just try to work with this map. So alpha A is this map sending every subset S of A to A minus S. This is what alpha A map does. And the map alpha A has been defined for every object A, right? So we have defined a natural transformation alpha. That is, we have defined a natural transformation alpha by definition is exactly a map that assigns to every object of your first category, in this case set op, a unique arrow in the second category. In this case the arrow is alpha A, which has, that is alpha is an arrow in set, so it should be a function. So the function alpha A has been defined in this way. So for every object A, you have obtained an arrow in set in the second category, which is alpha A, right? And alpha A is this assignment. So what you have is therefore a class of arrows. Oops. Yeah, what you have therefore is a class of arrows essentially. So alpha is this family of arrows. So 2 to the power A, 2 to the power A, alpha A, this family of maps in set, index over objects A in set op. What you need to verify to claim that this is a natural transformation? You need to check the naturality axiom. In other words, what you need to do is, so check. So for every arrow, so the domain category is set op, keep that in mind. So you should take an arrow S to T in set op. We'll write it as f op. So f op is an arrow from S to T in set op. For every such arrow in set op, what you want is your particular square to commute, right? So you have 2 to the power S, you have 2 to the power T, you have 2 to the power S to 2 to the power S, you have this component alpha at S, right? S and T are objects of set op. F op is an arrow in set op. So 2 to the power S to 2 to the power S, you have alpha S. 2 to the power T to 2 to the power T, you have alpha T. Now S to T, you have this arrow F op. So we have already defined what the functor 2 to the power gap does to an arrow in set op. It sends an arrow F op in set op to the arrow 2 to the power F in set. So this is your arrow 2 to the power F. This is your arrow 2 to the power F, right? You want this square to commute. This is what naturality means. So f op is an arrow S to T in set op, which means f is an arrow T to S in set, and an arrow in set is exactly a function. So f is a function from T to S in set. So what you just want to show right now is, given a function T to S in set, you want to show that this square commutes. What do I mean by saying that this square commutes? So this square in set, this is a square in the codomain category of the two functors. The two functors are exactly the power set functor 2 to the power gap. The codomain of the common codomain of these two equal functors actually is just set. So this is a square in set. You want this square in set to commute. What do I mean by this? I mean that 2 to the power f, this arrow in set, that is this function, composed with the arrow alpha s, which is again a function because it's an arrow in set, is equal to alpha t composed with 2 to the power f. These two functions should be equal in set. These two arrows instead should be equal. That is, you want these two functions to be equal, right? When are two functions equal? By the way, these two functions have their domain 2 to the power s and they have their codomain 2 to the power t. So when are two functions from 2 to the power s to 2 to the power t equal? If and only if they are equal at every element of the domain 2 to the power s, right? What is an element of the domain 2 to the power s? It's just a subset A of s, right? So this equal to this is equivalent to showing that 2 to the power f composed with alpha s applied on a subset A is equal to alpha t composed with 2 to the power f applied on a subset A for all subsets A of s, that is for all elements A in 2 to the power s, which is equivalent to showing. So what was the description of the map alpha s? How did we define the map alpha at s? Alpha at okay, this might be a little confusing for the notation because let's write this subset as x, sends it to a minus x. Yeah. So what is the description of the function alpha at s, or what is the description of the map alpha at s? It sends any element of the domain which is a subset of s to its complement, right? That is what it does. So you have taken a subset A of s. What does alpha at s do? It sends A to s minus a. So 2 to the power f applied on s minus a is alpha at t composed with 2 to the power f applied on a. What is 2 to the power f applied on a? What was our function 2 to the power f? 2 to the power f sends any subset s to f inverse s, right? So 2 to the power f a should just be f inverse a for all subsets A of s. So this is equivalent to saying that f inverse of s minus a, because 2 to the power f acts on s minus a in this way, is equal to alpha at t applied on this. Again, what was the map alpha at t? Alpha at t was defined in exactly this way. So this way, so here think of a as a dummy variable, that's all, right? You replace a by s once, you replace a by t once, right? So what does alpha at t do? It sends any element of its domain that is a subset of t to its complement, right? So alpha at t of f inverse a should be t minus f inverse a for all subsets A of s, right? And this is exactly what we had. So if this identity holds for any mapping T to S, that is just equivalent to saying that this alpha that you have taken here from the power set functor to itself, which assigns to every object A of its domain this arrow alpha A, that is this map alpha A, that is this morphism alpha A in the codomain, which which has been defined in this way, assigning to every x the object A minus x or the element A minus x. This map alpha A is natural in the variable A, or in other words, alpha is a natural transformation from the power set functor to itself, or this maps alpha A. So for every object A you have one map alpha A. This maps alpha A as A varies from the components of your natural transformation alpha. So alpha is this collection of alpha A's indexed over the objects A in set of. Alpha is a natural transformation, that's all that this says. So statement is equivalent to your given statement on your set theoretic statement is equivalent to saying that alpha from the power set functor to the power set functor, which is defined to be this collection of alpha A's from a set 2 to the power A to 2 to the power A, index over objects A in set of. What is this alpha A arrow? It sends every arbitrary element that is a subset S of A to A minus S, or rather let's say subset X of A to A minus X. This alpha A arrow sending any such subset X to A minus X, this alpha A arrow from 2 to the power A to 2 to the power A you have, and you have this collection of such maps or arrows alpha a, as a varies. So for every a you have exactly one arrow alpha a. So this collection alpha a is a natural transformation. From the power set functor to the power set functor. Okay, this is what your statement says. Those two are equivalent. We have only, I mean, we have proved that the naturality of your alpha is means exactly this. That is exactly your statement. So those two are equivalent statements. I mean, saying that this statement holds is equivalent to is just the familiar observe. I mean, saying that alpha is a natural transformation from the power set functor to itself is just equivalent to this familiar observation in set theory. Yeah, I think I have spoken too much and today, and let's stop today, and we'll continue next week. There are two problems. I want you guys to try at least. Let me see. So try both of them actually. So we'll just keep this as a practice problem. This is an interesting problem, by the way. Please do have a look and try it. And this is also a practice problem. This is this problem is fine. I mean, it's not that important, but I would ask you to definitely try this one. This is a conceptual problem. Okay. Yeah, let us stop here today. If you have any questions, write to me in my email ID, on my email ID, or you can just put up a question on the discussion forum as well. This is my email ID, by the way. Yeah, let's stop. Thank you.